This is the second installment of our second oscillator design case study. We're going to talk about the oscillation conditions. We're going to consider our oscillator as a one-port reflection oscillator, and in particular we're going to consider it as a conductance oscillator. If stable single frequency oscillation occurs, then the admittance of the tank circuit YR and the admittance of the device circuit YD will add to zero. Or in terms of the real and imaginary components, GD will be equal to minus GR and BD will be equal to minus BR. So GD, the device, will have a negative conductance, and BD will be inductive if BR is capacitive, or BD will be capacitive if BR is inductive. Now we look at the oscillator two ways during the design. We look at it in terms of its admittance or its components, conductance and susceptance, or we look at it in terms of reflection coefficient, and we switch between these two views as we start to develop our understanding of how we want our oscillator to work. Another way of looking at this oscillator, if stable single frequency oscillation occurs, then gamma R gamma D is equal to 1, and gamma R is equal to 1 over gamma D, or gamma D is equal to 1 over gamma R. Those three expressions for reflection coefficient are equivalent, and we pick the one that suits us for the particular design strategy that we're following. Certainly this gamma R gamma D equal to 1 is not the strategy that we find useful. Gamma R equals 1 over gamma D is useful, so if on a Smith chart we plotted gamma R and we plotted 1 over gamma D, then when we have stable single frequency oscillation, those two loci, the loci of gamma R and the loci of 1 over gamma D, will cross each other. That is the most useful way to look at it. Another alternative is to plot gamma D and 1 over gamma R. That is useful if our tank or resonator network has very little loss, but we can pick any of these views that we want. Now I've been quite careful in my words. I've said here that if stable single frequency oscillation occurs, then we will have these conditions. However, those conditions are not enough to ensure that we do have stable single frequency oscillation. We could have unstable oscillation, more of a chaotic behavior, or we could have multi-frequency oscillation. And so our oscillation conditions are in two parts. There is an oscillation condition, our first part, and we will talk about this in terms of variation of conductance and susceptance. This oscillation condition is known as the Kurokawa oscillation condition. And the second oscillation condition are the conditions that we require for startup of oscillation. And in both of these conditions we are talking about stable single frequency oscillation. So let's talk about the Kurokawa oscillation condition. The oscillation condition can be expressed as a formula. Here is the formula here. And this is the form of the oscillation conditions for a conductance oscillator. So let's go through and read through this description. This is saying that the derivative of GD with respect to voltage, so this is the voltage across the device as shown in that figure on the top right hand curve here. This is saying that the conductance of the device with respect to voltage multiplied by the derivative of the resonator susceptance with respect to frequency, so we have both amplitude dependence and frequency dependence here, minus the derivative of the device susceptance with respect to voltage times the derivative of GR with respect to omega must be greater than 0 at the operating point. Our subscript 0 refers to the operating. There's an additional assumption here that BR and GR are both independent of voltage. And of course that is what we normally expect. But in reality that may not be exactly the case, because our tank circuit could contain varactors, variable capacitors, to enable us to tune our oscillator. So we want to design our tank circuit to make sure that as much as possible the admittance of the tank circuit is independent of amplitude. The Kurokawa oscillation condition describes what we need to have a single crossing of gamma R and 1 over gamma D. For a fixed frequency RF oscillator, GR is very small, so the second term is negligible. So here is GR. For a fixed frequency oscillator, we can build very good resonators and our conductance can be very small. And if it is negligible, the second term is negligible. So the Kurokawa oscillation condition simplifies tremendously. In our first oscillator case study, we were making use of that without explicitly saying that that is what we were doing. In graphical form, and for a fixed frequency RF oscillator, this is what the Kurokawa condition is simplified to. So in the top curve here, we have GD with respect to amplitude. There's our amplitude there, that is our voltage. We have the conductance of the active device, in fact it's the negative conductance of the active device, falls off as the amplitude increases, and GR is very small. And we have to have a variation of BR with respect to frequency. Now the derivative, if we look at this curve here, the derivative of GD with respect to amplitude is positive, minus GD is falling, and so GD itself is increasing. It's going from negative to positive. If the derivative of GD with respect to amplitude is positive, in order to have this condition, that formula is greater than 0, we must have the derivative of the susceptance with respect to frequency increasing. So we must have this type of curve. So with a fixed frequency RF oscillator, we don't really care how BD or GD vary with respect to frequency. We will still obtain stable single frequency oscillation. However, this is only with a fixed frequency RF oscillator where GR is very small. For an RF VCO, GR is not small, and that is primarily due to the varactor loss. So design can be complex. For an RF VCO, unless we do something special, we will need to design using the full Kurokawa condition. And if you look up at this full Kurokawa condition, we have to manipulate the derivative of GD with respect to voltage, the derivative of BR with respect to frequency, the derivative of BD with respect to voltage, and the derivative of GR with respect to frequency. So there are 4 things that we need to deal with in design if we're dealing with an RF VCO. Now 4 things is not too much to deal with in design. We've done that with other types of design. But there are many other things that we need to accomplish as well. So let's spend a little bit more time talking about the Kurokawa oscillator condition for microwave VCO design. The full form of the Kurokawa condition is shown here. Achieving single frequency oscillation for a fixed frequency microwave oscillator can be a challenge, but the design complexity is so much higher for a microwave VCO. We find that design using the full Kurokawa condition is very limiting at microwave frequencies, and that is because there are other conditions that we must meet. We must minimize phase noise. To have a competitive VCO design, we must keep our phase noise very low, and the state of the technology is such that our competitors, if you like, or people in other research groups can do very well, so we must do very well as well. For example, we want the frequency of oscillation to be independent of the oscillation amplitude. That will minimize noise. Now there will be noise in our circuit. There are white noise generators in our circuit. That white noise will appear on the oscillation amplitude. If the frequency of oscillation is dependent on the amplitude and therefore responds to the noise on the amplitude of our oscillator, we will generate phase noise. Noise in the frequency domain, noise that results in a small frequency shift, looks the same as shifts in the phase, and it is interpreted as phase noise. So we must minimize phase noise. That is absolutely important. We must minimize the DC power consumption, and the reality is that oscillators have fairly low efficiency. Comparing the RF power coming out to the DC power going into the oscillator, the efficiency is really quite small, maybe a few percent. Of course, we could follow our oscillator by a fairly efficient amplifier and boost the overall efficiency, but the oscillator core itself is fairly inefficient. We must also consider the conditions for oscillator startup in our design. Considering all of these factors, minimizing phase noise, minimizing DC power, having the right conditions for oscillator startup, and then meeting the 4 conditions on the behavior of our susceptances and conductances that are implied by the Kurokawa oscillation conditions is really a little bit too much, especially if our oscillator is operating above a gigahertz or so. So the idea is to simplify the Kurokawa oscillator conditions. Now you can imagine in 5 years or 10 years we may become sophisticated enough that we can deal with the full Kurokawa oscillator condition for a VCO. Our CAD tools could evolve to tell us all of the information we need in a very simplified, compact form. But where we are at the moment, we must simplify a Kurokawa oscillation condition. So there is our full Kurokawa oscillation condition shown there. So we have to keep our design procedure simple, and this opens up the design space to enable optimization of other characteristics. Now it turns out that our experience is that if we simplify the Kurokawa oscillation condition, we're actually not giving up much in performance. By simplifying the Kurokawa oscillation condition, we have to make some changes to our circuit, but those changes do not seem to compromise performance much. Perhaps eventually we will figure out that we can achieve a slightly better performance with a bigger design space. You'd normally think that you could achieve a little bit more, but currently it doesn't seem as though that we would achieve that much more. So our microwave VCO design strategy is to choose a topology that, first of all, has an effective device acceptance that is independent of signal amplitude. Okay, so what are we doing here? We're looking at this right-hand term here, and we're going to set that to 0. For our fixed frequency oscillator, GR was very small, so that second product was 0 anyway. Well, now for our microwave VCO, we're going to follow a design strategy, in this case study, which sets that second product to 0. And we're going to do that by taking the effective device acceptance and making it independent of signal amplitude. So dBd/dV is equal to 0. We'd usually like that anyway, but with a fixed frequency oscillator, we didn't have to concern ourselves too much with that. But with a VCO at microwave frequencies, BD will tend to vary with signal amplitude. For one, we have nonlinear capacitors in our transistor model which vary with voltage amplitude. Now that is not enough. We must look at our loaded resonator and make sure that the conductance is independent of frequency. And so we're going to set dGr d equal to 0. If we're at fairly low frequencies, that is what we would achieve. But think of what our tank circuit is going to be. It is going to consist of an inductor in parallel with a capacitor. Or in the case of the VCO that we're looking at here, we will have a transmission line that is in parallel with a capacitor. And that capacitor is a varactor, and that varactor has significant series resistance and also conductance. And so there will be a GR dependence with frequency unless we take particular action to make sure dgr d omega equal to 0. Now we cannot set both of these to be exactly equal to 0, but if we make both of these derivatives approximately equal to 0, then our product term is going to be approximately 0 as well, even closer to being 0. So the Kurokawa condition for simplified design now becomes that simpler expression at the bottom. This is telling us that if our negative conductance becomes smaller in magnitude as the amplitude increases, that's what we expect, we will need to have a susceptance that increases with respect to frequency. We can use that simplified Kurokawa condition provided that the derivative of the device susceptance with respect to amplitude is 0 and the derivative of the tank circuit conductance with respect to frequency is equal to 0. And that is the design strategy that we're following here. So what does this look like graphically? Well, first of all, our design is such that our device network is set up so that dBd dV is equal to 0, and our tank network is set up so that dgr d omega is equal to 0. And graphically, this is what it looks like. We have a finite loss, and we're looking at a tank circuit that consists of a parallel LC, or a circuit that looks like a parallel LC circuit. And so GR will be as shown here. It will follow a line of constant conductance, because of course GR is independent of frequency. And so this is plotting gamma R with respect to frequency, and we are following a clockwise rotation on that line of constant conductance, because the conductance doesn't change with respect to frequency. Also, GD will change. Now GD is negative, so gamma D would be outside the unit circle of a Smith chart. And so here we're plotting 1 over gamma D. As GD becomes less negative as amplitude increases, so those purple lines with the arrow are indicating what happens to 1 over gamma D as the amplitude increases. As GD becomes less negative, 1 over gamma D, and also gamma D will become closer to the unit circle. Oscillation will occur when gamma R and 1 over gamma D cross at a particular frequency. Now that is one of the interpretations of that simplified Kurokawa condition, and that is the right interpretation to use when our resonator network has finite loss. Now recall the unmodified form of the Kurokawa condition. This unmodified form takes into account that the device susceptance can vary with voltage, and so we would not follow those lines of constant susceptance for 1 over gamma D. And it also accounts for the conductance of the resonator varying with frequency, and so we would not follow a line of constant conductance. An alternative simplified Kurokawa oscillation condition is shown here graphically. If the loss of our resonator network is very small, then our locus of gamma R is going to follow the unit circle. And so we could take this interpretation as well. Gamma R still moving in the clockwise direction can be as shown here, and 1 over gamma D will follow those purple lines there. As the magnitude of GD becomes smaller with increasing amplitude, 1 over gamma D will move towards the unit circle. And so we can use this interpretation for a fixed frequency oscillator with very low loss in the resonator network. That previous interpretation could be used with either a VCO with finite loss in the resonator network, or it could be used with a fixed frequency oscillator. But this interpretation shown on this slide cannot be used with a resonator that has significant loss. Or I should say you could use it, but you'd find design to be very difficult because the intersection is going to appear on one of these curves here. So if there's finite loss, we're going to follow one of these curves. And our intersection is going to occur in this region here. And very small changes in the conditions for the susceptance of the tank circuit is going to have a fairly big impact on the frequency of oscillation and on phase noise. That's not a problem when the loss is very small because we're just going to intersect with that unit circle. Here are the two curves again. For a fixed frequency oscillator with very little loss in the resonator, we could use either of these interpretations of the simplified Kurokawa oscillator condition, but for a voltage controlled oscillator which always has significant resonator loss at microwave frequencies, we need to design assuming that our gamma R and 1 over gamma D curves are going to be as shown on the right hand plot. Design is an iterative process, and so we start with a very simplified topology and we build up on that topology, adding more and more components to achieve our final design. This build-up of the design, the process of making our topology more sophisticated, may occur over years as we gain more and more experience. So let's look at the circuit that we're designing. The basic topology is as shown on the top here. This is a common base Colpitt's oscillator, and we have a resonator on the left here which consists of a parallel LC circuit. And we want that circuit to look like a capacitor at the oscillation frequency. We want that resonator network to have a resonant frequency perhaps a little bit less than the frequency of oscillation. The particular form of the oscillator that we're going to design in this case study is as shown on the bottom here. We've arrived at this transmission line resonator here to replace the inductor in the simplified topology. That transmission line has lower loss. You may also notice that this transmission line is tapped. We can model this transmission line as a transmission line from the top to that point. Then there's a connection that goes off to the right to the active network, and a connection that goes down to another transmission line. In a lumped element simulation of this circuit, we would just consider two transmission lines to model TL1. Now the big characteristic of our varactor circuit, and our varactor circuit enables us to vary a capacitance by changing the tuning voltage V-tune. The particular characteristic here is that we have stacked the varactors on top of each other. Remember that one of the things that we want is that we want the derivative of BR with respect to amplitude to be equal to 0. A varactor on its own, if we just took one of these varactors on its own, this varactor has a capacitance that varies significantly with respect to a large RF voltage swing. By stacking these varactors on top of each other, we're reducing the dependence of the susceptance on the amplitude. So this stacking idea is used commonly in many different microwave circuits. So this stacking has enabled us to take our derivative of BR with respect to amplitude down to something very close to 0. And that is exactly what we needed to do in order to use that simplified Kurokawa oscillation condition. We're going to talk more about the active device later on, but one of the things that we want from our active device is that we want the susceptance of our active device to be independent of amplitude as well. And we've added a few components here, in particular CA and CB, as extra design variables that we can use to make sure our active network has our idealized behavior. Many of these other elements provide RF short circuits or RF open circuits. Of course, we have to bias our transistor here, and so we have to provide provisions to enable us to bias our circuit but still let our RF signal get through. Shown here are two graphical representations of the simplified Kurokawa oscillation condition. And we have to decide where we want oscillation to occur on these Smith charts. That is, we want to decide where we want the point of oscillation. And the point of oscillation will be where gamma R and 1 over gamma D intersect for the same amplitude and frequency. We're dealing with a Colpitts oscillator, and so the top half of those curves are going to be eliminated. Now we could decide our point of oscillation to be in that region 1 shown there, and that's a very good choice for a fixed frequency oscillator. Or we could choose our point of oscillation to be in that region 2. For a fixed frequency oscillator, either region of oscillation is suitable. Of course, with a fixed frequency oscillator with very low loss in the resonator network, the locus of gamma R is going to be on the unit circle. For a microwave VCO, region 2 is required, and that is because of the resonator loss. We could get a VCO to operate in region 1, but because the curves end up becoming so close together, we're going to find that we're going to compromise our oscillator noise performance if we deal in region 1. I'm sure that there are some microwave VCO designs that operate in that region 1, but I'm sure they don't have as good a performance as the oscillator that we're going to design here. The VCO oscillator that we're designing here in this case study, we actually built, and this oscillator has state-of-the-art performance, and if you use the right set of metrics, it still has the best performance. So let's talk about the resonator network for now. I've already said quite a lot about this resonator. We have inductors that are RF open circuits. We have stacked varactor diodes that help ensure that the derivative of BR with respect to amplitude is very close to 0. We have DC blocking capacitors here. This provides an RF short circuit. The capacitor on the bottom left there provides an RF short circuit, and the transmission line looks like an inductor that's in parallel with the capacitor. So when you start taking out some of those elements that are simply RF shorts and opens, and we forget about the DC concerns, we have a varactor that's in parallel with the transmission line, and that transmission line is tapped just so that we can provide some additional impedance transformation. The susceptance of our resonator network will depend on the tuning voltage V-tune attached to our varactor diodes. On your own, you can work through the biasing of our varactor diodes and see that each of our diodes has a voltage V-tune across it. So if we set V-tune equal to 1 volt in this case, you can see what our gamma R looks like. We start off at 3 gigahertz here, and after 1 gigahertz we get to this 4 gigahertz point here, and then as we're in resonance we very quickly move around to this 5 gigahertz point. We have a circuit that is essentially a parallel LC circuit, and at resonance that will look like an open circuit, and our open circuit region is around here. Gamma R at 1 volt very quickly goes from 4 to 5 gigahertz, and our region of oscillation is going to be around here. This will be our point of oscillation, the region in which we're going to try and design. When we change the voltage across those diodes, our resonance curve is going to change. What I've plotted here is gamma R at 1 volt and gamma R at 3 volts. And I've indicated the frequencies on these gamma R loci for several points in the interesting region every 0.1 gigahertz. And you can see, let's just focus on this region down here. You can see on one of our curves, our 1 volt curve, we have a 4.5 gigahertz, and for the 3 volt curve we're at 4.8 gigahertz. So if this region down here was our region of oscillation, you can see that by changing the tuning voltage we're going to shift the frequency of oscillation. So gamma D is going to be somewhere out here. 1 over gamma D is going to be inside, in this region here, inside the unit circle of the Smith chart. Let's do some comparison of our oscillation points. In our oscillator case study, the point of oscillation was in this region. Gamma R stretched from 15 gigahertz to 20 gigahertz. So over a 5 gigahertz region, gamma R did not change very much. We were relying on the susceptance of the active device varying strongly with frequency so that we could set the frequency of oscillation. And we could get away with that with a fixed frequency design because the derivative of GR with respect to amplitude was very small because GR was very small itself. We cannot rely on BD varying with frequency to enable us to shift the frequency of oscillation with a VCO, because we must have the derivative of BD with respect to frequency being very small using our simplified Kurokawa oscillation condition. So in case study 2, we must be in this region here. Now, strictly speaking, for a Colpitt's oscillator, we would have to be below the horizontal line of the Smith chart. But we can cheat a little bit here because we don't actually have an inductor there. We have a transmission line there. Things are a little bit different. So the region of oscillation can be a little bit inductive as well, as long as we get stable single frequency oscillation. But there's quite a difference between the two designs. One, the point of oscillation for our first case study is this very small region on the left, and we're relying on the susceptance of the active device to vary with respect to frequency to give us a little bit of extra adjustment. But in our simplified Kurokawa conditions, and the choice of using those is a result of the significant loss of the resonator, we must achieve most of our frequency variation by varying the resonator network itself, because we really want our active device to be fairly independent of frequency. Now we can put that requirement in a much more formal way, maybe a little bit harder to understand way, by considering this curve here. Now this curve plots the parallel resistance of the tank circuit versus gamma D. So we have curves A, B, and C here for different gamma D. So this is saying that if gamma D is equal to 4, so that would be at a very small signal, we're producing a very large negative conductance, or I should say a large in magnitude negative conductance. And this is saying that our RP for our curve C must be at least 70 something ohms, 75 ohms or so, or 80 ohms, in order for us to have oscillation. So our oscillation condition requires us to have a magnitude of GD that is greater than GR. That is, we want GR to be small or smallish. In order to have a small GR, we must have a large RP. So in order to have oscillation, we must have a high RP. RP is equal to 1 over GR. So for oscillation, we want a high RP, so GR must be small, which means that we have to be in that region. So that is the reflection coefficient of the active device. We would like the reflection coefficient of our active device to be somewhere between 0 and 40 or 50. We want to be in this region here. That means that we want GR to be between 0 and minus 60 degrees, That's the same as saying that we want gamma R to be in that slightly capacitive region. So summarizing, there are 3 points here that we have made. One is the full Kurokawa condition for stable single frequency oscillation for a one-port conductance oscillator is as shown here. For a fixed frequency oscillator, GR is very small, so that second product term is essentially zero. For VCO design, where the resonator is lossy, we must make a design choice. Not everybody will make the same design choice, but this is the design choice that is made in this second oscillator case study. We will use a simplified Kurokawa condition because it is easier to design to. In order to use this simplified Kurokawa condition, we must address these two derivatives. We want the susceptance of the active device with respect to voltage to be zero, and we want the derivative of GR with respect to frequency to be equal to zero. In the next installment, we're going to talk about how we take these derivatives to zero. For a voltage-controlled oscillator with significant resonator loss, we consider this behavior of gamma R and 1 over gamma D. And the region of the Smith chart that we choose for oscillator startup is in that lower right-hand quadrant. And we have to be in this region, one, because we're doing a Colpitts design, and secondly, we have significant resonator loss, so our gamma R locus is not going to be anywhere near the unit circle.